Hey everybody, welcome back. So this is a little bit off the subject here from the BA 2000 series that we're doing, but I thought it would be an interesting thing to do. I've been kind of working on this project on and off for a while, and it's just a new piece of test equipment that I'm going to put on the bench. And I have it finished up, and we're going to do some tests on it. And I have some clips kind of cobbled together of the process of going through this. So I'm going to share those with you in this video, and then we're going to do some testing on it to see how you test it and what it looks like. And we're going to get to see the Instech MDO2204EX, some of the more advanced features that it can do. And I think that'll be kind of interesting to watch. So I warn you up front, I'm still having some issues with the video with these cameras. I'm probably going to end up going back to something more like I was doing before. I have a video that I'm going to release here very soon on the BA 2000, and about the first 8 or 9 minutes of it is me ranting about the camera. And I know a lot of you people don't like hearing people complain or being negative. And I hate that too, by the way. It's a hypocrite here doing that. But really, I thought I should let you all know what I'm going through with it. Things are very busy at work right now. I am extremely busy. And so I have limited bench time. So I kind of want to maximize the time I have down here and do more on working on the things I love rather than trying to be a photographer, which I'm not. So I wanted to share that part with you. So what we're going to talk about today is a pink noise generator. And what is pink noise? Well, first of all, what's noise? Noise is any type of interference, unwanted interference. But in the audio world, noise is a certain set of frequencies that are being played at the same time on top of one another, and depending on how the energy of each frequency is distributed will determine what type of noise it is. So for instance, the most basic kind of noise is called white noise. White noise is all the frequencies from 20 hertz to 20 kilohertz, at least in the audio world, and they're all played at the same level. So each frequency has the same amount of energy per frequency. So 1 kilohertz will have the same amplitude and energy as 10 kilohertz, as 20 kilohertz, as 10 hertz, 20 hertz, whatever. That's white noise, okay? The other type, and what we're going to be interested in, is a type of noise called pink noise. Pink noise is when you take white noise and you run it through a filter, okay, a LC filter, or actually an RC filter in our case, and you're going to have those same frequencies, only they're going to be distributed by energy kind of logarithmically per octave. So that means each octave, each additional octave, there will be a minus 3 dB loss or attenuation. So what does that mean? What is minus 3 dB per octave? I'm not doing a good job of my vocabulary here because it's kind of late and I had a 17-hour day yesterday, so I'm a little bit punchy here. But anyway, so for instance, if we talk about 20 hertz, an octave of 20 hertz would be 40 hertz. So from 20 hertz to 40 hertz is 1 octave. And so from 20 hertz to 40 hertz, you should see a 3 dB, minus 3 dB attenuation. So that means if the 20 hertz is 0 dB, with reference to a volt, let's say, the 40 hertz will be minus 3 dB or 3 dB down from whatever the 20 hertz is. And this gets distributed per octave. So of course, as you get higher in frequencies, you get higher in octaves. So for instance, an octave of 20 hertz would be 40 hertz. And just the difference between 20 hertz and 40 hertz is only 20 hertz. So over a 20 hertz range, you're having a really steep roll off of minus 3 dB. However, with higher frequencies like 10 kilohertz, 1 octave of 10 kilohertz would be 20 kilohertz. So from 10 kilohertz to 20 kilohertz, there will be a minus 3 dB. And so you can see that's a 10 kilohertz range of frequencies and with only a 3 dB loss. So you can see how that, if you drew that as a curve on a linear scale, you would see the 20 hertz be way up here, and then it would make this steep slope, and then it would gradually kind of curve off till it turns into a gradual slope down to 20 hertz or 20 kilohertz. You'll see that. Why is that important, you might ask? Well, our human ears hear logarithmically. In other words, if you played all of the frequencies at the same energy, like white noise, it's going to sound really harsh. It's going to sound really shrill and kind of hissy, because the high frequencies will have will at least give us the impression that they are louder than the low frequencies, even though they're all at the same energy level, if that makes sense, or the same output. And that's because, in 1 octave of high frequencies, there's a whole lot more energy than there is in 1 octave of low frequencies. So if you listen to pink noise, it doesn't sound so shrill. It actually sounds kind of like you're standing next to a waterfall or something like that. And that is a more natural way our ears respond to sound pressure. So pink noise is a very important signal to pass through audio gear for testing speakers, for testing amplifier response and things like that. And we've never really done that on this channel, so I'm kind of excited about it because I want to do some tests with it. Now there's other types of noise. There's different colors of noise. So there's pink noise and white noise. And of course there's brown noise or Brownian noise. Don't get the two confused. Brown noise is the noise you hear when you pull grandpa's finger. No. But anyhow, really all the different types of noise have to do with how the frequencies are distributed versus amplitude or energy, let's say. So that's just a quick synopsis of what that is. And believe it or not, generating pink noise is not so easy. It's easy to generate white noise. And most signal generators, and you'll see this on the DG4162, my Rigol, they can produce white noise pretty well. But if you need to produce pink noise, it's not so easy, because you have to really get it properly calibrated to get that 3 dB per octave roll off. And that's what our little project that we're building is going to do. So let's just get into this, and I'm going to go through some old clips that I made a while back. So you'll see the video change, kind of the lighting and what's on the bench and things. It's because I did this over a period of time and I'm stitching everything together. So what we're going to do right now that everything's done, I'm going to do a couple of tests and things, and those will come towards the end of this video. If you go back a couple videos, I made this little project here, and this is a difference amplifier. And we use it to monitor input versus output, or one channel versus another channel. Check out the videos on it. It's pretty interesting. Now, another thing that would be helpful that we could possibly use with that difference amplifier is a pink noise generator. Now, why would you want noise in the first place? What advantage is there to having a noise generator? Well, there's several reasons. Number one, a lot of stereos you buy today that have built-in calibration for your sound in your room will generate a pink noise signal. And it'll put that pink noise signal into your speakers. Your speakers will actually create sound pressure waves in the air that you will hear. And you can use a calibrated microphone, and you can measure how those sound pressure waves propagate through the air in that room that you're in. And you can fine-tune the frequencies to get that 3 dB per octave that you're looking for. That will give you the ideal listening conditions for listening to recorded media for your ears. Now here's where it gets kind of crazy, is that that is in a perfect world with perfect ears. Some of us have, hearing loss at certain frequencies, and that may not always sound good to you, if you have hearing loss, and you may need to shape that curve differently. But the whole point of it is, when you put that pink noise signal out, you can actually tune all of the frequencies at once to sound good to your ear. Once you learn what pink noise sounds like, it's very easy to identify when it's correct or not correct. And that takes a little bit of experimenting and listening to. Now, as far as electronics is concerned, it's very important because you're reproducing that whole energy, that energy curve at 20 hertz to 20 kilohertz, which is our hearing range generally for healthy ears. Some can go a little outside of that range, but most of us, that's the general rule of thumb. And this pink noise generator helps us to understand, or to visualize how an amplifier or how an piece of audio gear handles that. So it's a useful piece of test equipment. Think of it as a fancy signal generator. And I think you'll also see that a lot of signal generators out there, very expensive ones, some of them, can produce somewhat of a noise signal, but they don't have the control that these do. So it's good to have a standalone pink noise generator. Now, how do you create pink noise? You create it by making a white noise generator and then putting a 3 dB per octave filter at the output. So that's what this is. We'll get into that in the schematics here in a little bit. So let's look at this kit. There's a couple ways to produce the noise signal that you need. In this instance, white noise, that we're going to convert to pink noise. One way, and I'll show you a schematic of the simpler way to do it. So one way is by just taking advantage of the flaw, inherent flaw in a transistor. And the other one, you know what, I really don't like this white balance. Let me fix that. Okay, we'll see if that's better, if it hunts more or less. But anyway, there's two ways to do it. One is just analog, and that is by using a noisy transistor to make that noise. The other way is a digital way, and the math that goes into how it happens is very complicated, and it's definitely outside of my wheelhouse. I just know that it works. And you do that by using shift register ICs, which are very common and cheap to buy, and a clock. You create a clock with certain frequency, and you can make that pretty exact frequency spectrum. And if you do it with enough steps and you put the right filtration on it, you can get a pretty good representation of a pink noise signal. That's what this is doing. And it looks deceptively simple, this tiny little board. The math behind it can be, at least to me, a little bit confusing. So let me show you the other way to do it if you don't want to do this. And this is a kit you can buy. It used to be, what's the name of that company? I forget their name. Velleman, right there. And I'll show you. You can take a look if it'll focus. See Velleman. And they got taken over by this company called Wada. I hope I'm saying it right. They now own Velleman, and they still make all the same kits, just different name. You can buy these online. They're not very expensive, and they do a very good job. Let's take a look at another method, though. Okay, so let me get my chopstick. So here's a very simplified drawing of how to create a white noise signal. And that is, you take a transistor and you put it in reverse bias. You put enough voltage between the base and the emitter in reverse, and something strange happens. It starts creating a hiss or a noise. And it just so happens to be white noise, a pretty good source of white noise. It's very random, and it's within the frequency spectrum that we need for audio. And all we're doing is we're kind of current limiting it so we can't overdrive this. And you're just taking a voltage, and it can be plus and minus 12, plus and minus 9, anywhere. You have to experiment with the voltage. And you can see I made a note. You really have to experiment with you have to hand pick the transistor. So you can use like a BC548. You can use a 2N, what is it, 3906, I think, or 3904, whatever the NPN is. Any number of, and just the small signal NPN transistor. And different ones will create noise better than others. Like I wouldn't use an ultra low noise transistor like a KSC 945 or 1845. Those are low noise. They're intended to be low noise. You want a more basic, like 2N2222, something like that. And even those are going to have varying degrees of noise. So you have to have several of them to try. But if you do that, you'll make that noise signal right here. And then if you just run it into a simple op amp, like a TL072 or anything, that just a JFET input with real high impedance, that's the main thing. You want it to be a real high impedance input. It'll amplify that noise, and there you go. And this is just set up as just a basic non-inverting amplifier. And that's it. You create noise. It's really, really simple. Now, this is going to be white noise when it comes out here. And then to put that roll off onto it, you're going to have to put a series, and a capacitor will roll off naturally at 6 dB per octave. Okay, you don't need to know all this stuff, but I'm just kind of explaining it. So in order to get a 3 dB per octave roll off, you have to have a series of stepped filters, those stepped 6 dB filters at certain intervals, and it will mimic a 3 dB per octave roll-off. And the more stages you put in there, the more accurate that roll-off will be. But if you get it approximate, it'll be good enough for what we're trying to do. Conversely, these digital ones are the same thing. They still create white noise, and then you have to still run them through a filter to get the pink noise. It's just the way it works. It's nature. It's just electronics. It's the way it works. So, and of course, there's other ways you could do it using digital signal processing and so forth, but that's way too complicated, and we don't need that. And it's strange, but a lot of these signal generators that are out there, like my Rigol DG1642 is a really expensive signal generator, but it cannot naturally on its own produce true pink noise. It has a noise function, but you still have to run it through filters and everything to get it to be pink noise. Now, if there is a way to do it on the DG4162, I couldn't find it in the service manual, in the owner's manual. And I did check a few of the forums and things out there, just did a search, and I couldn't find anything on how to do that. My GW Instech, mixed domain oscilloscope, same thing. It has a built-in signal generator that's pretty decent. Not as good as the 4162, I don't think, but it's a decent one. I don't think it can do it either. So this is the easiest way: a transistor and a op amp, or buy one of these digital kits. And these are a lot more consistent. Gives you consistent inconsistency that's predictable impredictability. Yeah, I know, it's weird. But it's random, and it's called pseudo-random. This is totally random noise. You never know what noise, what the noise signature will be from one split second in time to another. Whereas this one will give a repeatable pattern of noise, but it's so mixed up that you won't notice it. So it'll sound like it's random noise, but it's actually not. We call it pseudo-random. So a lot of talk about things, but just to give you a background on what this is, because really building this can take me a couple minutes. It's, a half hour or something to solder these parts together. And then we'll test it out, and we'll look at it on the spectrum analyzer at exactly what it does. So let me get this put together, and then we will do the spectrum analyzer. and see if we have a good pink noise generator. Oh, and in case you're interested, here's the schematic of this little pink noise generator. Pretty simple. You have an oscillator here, and then you have these shift registers, and then down here you have a kind of a buffer transistor for the output, and here's your filter network. And what they're doing is they're showing these dotted lines because you can actually modify a few of these components and convert it back from a pink noise generator to a white noise generator if you so desire. And that's all these dotted lines are all about. So it just changes the roll off of the spectrum. But again, I'm not going to pretend to understand the math between how these shift registers work to do this, because it's just not something I ever studied that closely. But anyway, you just need a basic input of like somewhere between 9 and 15 volts DC, single rail, and you'll get your output. So let me build this. Okay, that was rather easy to assemble. And the calibration is pretty easy. You just want to adjust RV1, which is this pot right here. And I put a 10 turn in here because a single turn is kind of going to be a little bit too coarse, I think. I mean, sure, it could be done, but... And what they want you to do is they want you to have a flat reproduction characteristic as possible. Especially pay attention to the higher frequencies. So essentially what they're saying is, if you're looking at this on a real-time analyzer, an RTA, you're going to want to set this to be a flat line across the scale. So like all of the individual frequencies should all be the same, because an RTA actually scales that 3 dB per octave for you. Now, I'm going to use an actual spectrum analyzer. I'm actually going to use the spectrum analysis program on my MDO 2204. And so as a result, it does not display, it does not add that 3 dB per octave attenuation into its measurement. It actually measures in a linear way and displays it in a logarithmic way, if that makes sense. So you'll see that. So what we're actually going to do is we're going to set ours for a curve. And I want to set 1 octave, so I'm going to go at 10 kilohertz. From 10 kilohertz to 20 kilohertz, I should have a 3 dB drop. And that's what I'm going to try to adjust this pot for. So let's get lined up to the scope, and then I'll hopefully you'll see what I'm talking about. Okay, so what you can see is this is the spectrum from 0 hertz to 20 kilohertz. 10 kilohertz is the middle of the screen right here. So from here to here, I want to see a 3 dB drop. Right now, just out of the box, the way it is, it's going from here down to here. And this is 10 dB per graticule. So that's looking at almost a 15 dB drop. So we need to adjust it. So all I'm going to do is I'm just going to turn the pot. And I don't know if I can do a picture-in-picture thing with you. I'm not going to mess with that. You just take it on my word. I'm going to rotate the potentiometer. And this white line is an average of the spectrum. Makes it a little easier to see where we are. So I'm just going to start turning this and see what happens. There we go. And let's let the averaging catch up. We want it to be roughly halfway in between there. That's going to be 5 dB. Just a little bit above halfway. So you can see that already did it somewhat. So let's bring it up a little more. Right about there is going to be pretty close. And the idea is you don't really want to see any bumps in there either. I'll go a little bit the other way now. Again, this is not going to be perfect, but it's going to be pretty close. And you have to let it average. It's kind of slow because the scope just can't process that many data points that quickly. And that doesn't look too bad there. Okay, I'm now plugged into the stereo analyzer. Just because it has a little built-in amplifier, we can listen to this stuff. I'll put the microphone next to the speaker here on the side. I just have it feeding into the left side, and you can see the signal, and you see how it kind of jumps around. And that's going to do that because there is a repetitive pattern to the noise generator. That's just the way it works. But let me hold the microphone here. I'll turn this up. And that is your pink noise. You can see the thing's only drawing 1 milliamp. I mean, it's almost nothing. So it's very, very low current draw. So this can be run on a battery pack very easily. And the batteries would probably last a very long time. So I may make the case big enough to put batteries in it. And then I could have a portable unit. And of course, I may even put just a couple resistors and make a splitter so that you'll have 2 outputs instead of 1. Or I might just use my signal generator splitter externally and just use a single connector. I'm not sure yet. We'll see the finished product later. Okay, so you can see on my Rigol I've selected something that you haven't seen me use before, and that is this noise button here. And you can see it draws a picture of noise, because that's kind of what noise looks like when you're looking at a spectrum analyzer or whatever. The other thing I need to talk about, and I'm not going to set it up, is there's different types of spectrum analysis you can do. So spectral analysis can be done with a standard spectrum analyzer, which is what we're going to use with the Instax. But you can also use what's called an RTA, or a real-time analyzer. And that is done through capturing this signal on your sound card of your computer. And then you can use some computer software, and it will show each octave of frequencies, or however you want it, every 10 hertz or whatever. And it will actually it actually puts that pink noise correction file on there. So basically, pink noise will look like a straight line. And white noise will kind of look like a curved line. And it does that on purpose because it's calibrated off of pink noise. And you can do all kinds of things with RTAs. And again, I have the software and so forth. It's a little bit of a hassle with my setup to get it to work properly, because you have to worry about distortion and things like that with using a sound card and using cables and all these things as I bang the camera. But one day when I get the time to fiddle with it, I'll show it to you. It actually works really well once you get it up and running. But we're going to do it the traditional way, using a standard spectrum analyzer. And, well, not a standard one. We're going to do a mixed domain oscilloscope, which has a spectrum analysis function. So I have it selected. It's just a regular white noise signal, and it's a 200 millivolts RMS. Okay, so I'm going to start out with it off, okay, and I'm going to get you on the scope, and then we'll take a look at what it looks like. Okay, so you can see I have this set to spectrum analyzer mode, and just so you see the difference, this is oscilloscope mode, and I can turn that off. There's your standard oscilloscope. Let me turn the signal on. And that's what it looks like on an oscilloscope. And this is looking in the time domain, because we're in oscilloscope mode. And if I go to spectrum analyzer, I have it set up to average out the signal. So it kind of gets rid of all that fuzz. These are some things you can do. Like I can turn the spectrum traces. That's kind of what you were seeing in the time domain as well. This is a really cool scope. The more I use it, the more I like it. It has a lot of limitations because it can't do anything perfectly, but it does everything adequately and does it pretty well. As a spectrum analyzer, a digital one, it's basically taking the FFT and just making it look like a spectral display. But it works. It works well. I mean, I'm not complaining. It does a good job. So anyway, I'll turn that off so we can just look at the averaged signal. And you can see this part here is 20 hertz and this is 20 kilohertz. So this is we're looking in the frequency domain now. And you can see all frequencies are pretty much randomly the same. This is called random noise, and that's exactly what it is. And you'll see that these will jump up and down, but they're all pretty much averaged out. If you drew a line through the averages of all these, it would make a straight line. So there's equal energy is what we're saying across the whole spectrum. Okay, now here is our new pink noise generator. And I'm not sure from the last clips that I did a long time ago what all I said about it, but this is not a stereo output. So there's different types of pink noise generators. The best one is the ones that can put out stereo pink noise that's uncorrelated. What does uncorrelated mean? It means that left and right channel will be random from one another. In other words, they're each going to be random noise, and that randomness is different between the two channels, if that makes sense. Whereas this one just has a single output that's split. So even though you can drive a stereo amplifier with this, each one of these is getting the exact random noise the same way. So that would be called correlated noise. So this is a correlated pink noise generator. And it's really a single pink noise generator. There's not two generators. I'm just splitting it off with a couple of resistors. And this is just a BNC jack so that you can connect it to test equipment leads and things. Or I can connect RCAs and go into an amplifier or a preamp to test it. So we're going to plug this in and we're going to turn it on, and it's all calibrated. And I think I did that in previous clips. So there it is, turned on. And this one runs on a battery pack. And looking at the scope, you can see just what I was talking about at the beginning of the video. So you can see 20 hertz, we're all the way up here. Okay, we're clear at the maximum. It does, zero, we'll call that 0 dB. And then you can see in the first, this is 1 kilohertz. Or 2 kilohertz, so it's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 kilohertz. So you can see in the first 1 kilohertz, look how much of a drop there is, because it's 3 dB per octave, remember that? So if we go into the center of the screen, where it's 10 kilohertz, if I go from 10 kilohertz to 20, you can see just a very slight drop. It's 3 dB, or minus 3 dB, I should say. Each one of these blocks represents a minus 5 dB down. So minus 5, minus 10, minus 15, you get the point. So I can turn on cursors. Let's see here, cursor. There we go. And I can actually measure where I have these cursors set to be 3 dB apart from one another. And if I put this top line right on where, right on 10 kilohertz, you can see right at 20 kilohertz, the second one is 3 dB down. So it measures perfectly. Now, what do you think happens here to go from 2 kilohertz to 4 kilohertz? Because that's 1 octave also, right? So let's put this top line right in the middle of 2 kilohertz. There we are. And you can see right at 4 kilohertz, we're right pretty close to 3 dB down, roughly. It's not perfect. And remember, the signal, the generator circuit that I'm using, it doesn't have enough stages in the filter to make it perfect. The more stages you put in your 3 dB attenuator filter, your octave filter, the more accurate you can make this. But you can see it's very close. It's close enough that it'll work for what we're trying to do. So that's it. That is pink noise. Okay, so you can see I've disconnected the BNC cable from the scope and connected this to the stereo now, and it's just going over to my receiver. And if I turn it up, I will hold the microphone next to a speaker. That is pink noise. How about it? Pretty exciting, huh? Okay, so I now have this connected to the signal generator up here, and it's set to put out white noise. And no, my Rigol will not do pink noise. Like I said, that's kind of hard to generate true pink noise with a signal generator. And if I turn that up and hold the mic in front of the speaker, it's going to sound very different. Did you notice how shrill and how high-pitched that static was, that noise sounded? And did you notice how lacking it was in low frequencies, in like the bass frequencies? Believe it or not, every one of those frequencies was being played at the same volume over top of one another, but our ears perceive that differently. In other words, we are more sensitive to the higher frequencies than we are to those lower frequencies. And so therefore, to us, we're hearing the high frequencies more easily than the low ones. And it's also the way that sound propagates through the air. It's a lot harder to move. You have to move a lot more volume of air for the bass or for the lower frequencies to get through there. So I hope that was just an interesting little experiment. We're going to play around with this more later on and see what we can do with it. And when I say we, I'm going to see what we can do with it too. I'm curious. There's some things I've read about, some other things I just wonder about and really haven't read anything about. And I want to try them in some of our restoration videos. I think it might be a nice deviation from some of the standard put a 1 kilohertz signal in there or a swept signal in there and read the distortion and all that crap. I think it would be very interesting. The other thing is we will be able to look at distortion on that scope as well. If you want to see more of the MDO 2204, let me know and I'll show you some more functions of it, because it's really a fascinating or a really good piece of test equipment. But that's it for this video. Hope you enjoyed it, and more to come very soon. In the meantime, I'm going to wish you all peace, joy, happiness, and good health in your lives, and we'll see you for the next video. Stay well, everybody. Bye-bye.